Hey everyone, welcome back and let's write some more Leetcode today. So today let's solve the problem number of good paths. This is definitely a hard problem. Do not underestimate it, but I'll try to explain it the best I can. We're given a tree, and the good thing is they do clarify what a tree is. It is a connected, undirected graph with no cycles. The fact that it has no cycles is going to be pretty important. We have n nodes. Each one of them is numbered from 0 to n minus 1. This is going to be important because that's how we're going to be able to uniquely identify each of these nodes. But it's a little bit confusing because each of the nodes has a second value, which is like the true value for the node. The way we can get the value of each node is we're given a values array, and we can use the label, the unique identifier of each node, and then map it to the actual value. From now on, I'm going to refer to this as like the index of every node. We're also given a list of edges connecting A to B and B to A. Remember, these are undirected edges. So when we're given an edge like this, that means 1 can go to 0 and 0 can go to 1. A good path just has a couple conditions that it has to follow. First of all, the starting node and the ending node have to have the exact same value. We're not talking about the index, we're talking about the actual value here. First of all, if we didn't have any duplicate values, we probably wouldn't have any good paths to start with. In this case, do we have duplicate values? We have 2 1s and we have 2 3. So does that mean this is a good path and that this is also a good path? Well, there's actually a second restriction. All the nodes between the starting and the ending node have to have values that are less than or equal to the starting node. And of course, the ending node has the same value. So basically, every node in between these two has to have a value that's less than or equal to, like, the starting value, 1 in this case. There's only one node in between them, and it has a value of 2. So in this case, this is not a good path. We can't do it. What about this other one over here from 3 to 3? Going through the 2 nodes in between them, there's a 1 here. That's good. It's less than 3. There's a 2 here. That's good. It's less than 3. And that's pretty much it. That means this is a good path. And all we really need to do is count the number of distinct good paths. One thing that they do clarify for us is that we can't double count, meaning we can't say that this is a good path and then going in the opposite direction is also a good path. So that's something we have to keep in mind, but that's not super complicated. So there is a naive way to solve this problem, which is n squared. Let me briefly discuss that. The easiest way is to basically go through every single node. Let's just say we arbitrarily start at this one. Let's see how many good paths we can determine starting at this node. I think we could probably do it with a DFS or a BFS. Let me briefly discuss how we could do it with a BFS. Basically, we would just run breadth first search. So go layer by layer. We'd check we're starting at this node, but its value is 1. Can we go here? Well, no, there would never be a good path. We're starting at a node with a value 1. So we're looking for other nodes with a value of 1. And we can't really have a 3 in between there, so we can't go in this direction. Let's try to go in this direction. Can't do it. So we couldn't find any good paths starting from here. So then we would go to another node from here. Let's see how many good paths we can get starting from here. We're allowed to go here. It has a value smaller than 3. We're allowed to go here. It has a value smaller than 3. We're allowed to go here and we're allowed to go here. This is our next layer, but this is basically a dead end and we never got to another 3. Here, though, is another 3. It's also a dead end, so we can't go further, but we did find a good path. So what we're realizing is we're going to have to run BFS starting from every single node. In the worst case, BFS is an n-time algorithm where we have to iterate over every node in the graph, and we have to do it n times, so that's obviously going to be n squared. It's not a bad solution, but we can do better. It's not easy to come up with the solution because you have to be greedy, but you also have to use an uncommon data structure called the union find data structure. I won't go super in depth into this data structure because this is such a hard problem. I don't want this video to be super long, and I think I have a pretty good explanation on this problem in Leetcode 684. So search for that video if you want to learn more about union find in depth. But basically, it's a way to determine if a set of nodes is connected to each other or not. Keep in mind that this graph does not have any cycles. So there's only going to be one unique path from duplicate nodes anyway with duplicate values. There's only going to be one path connecting them. There's never going to be a second path like this because that would mean we have a cycle and we can't have cycles in this graph. That's basically given to us. So how can we use this information to our advantage? Well, basically, we're going to be greedy. What do I mean by greedy? Well, we're going to start with the smallest values and then work our way up. So what we're going to do is sort all of the values that were given. But if we do that, we have to have a way to map the value back to the original node, like the index of the node. But we know we could have multiple nodes with the same value. So for example, when we create a mapping, we'll have something that looks like this. For the value 1, so we're going to map value 1 to all nodes with that value. In this case, we have 0 and we have 3. Those are the indices, so 0, 3. What about the next value we have is 2? We're going to map it to all nodes with that value. It's just a single one, 2. And then lastly, we have a value 3 and we have 2 nodes with that value. The indices of those are 1 and 4. So we'd create something like this. Then we would be greedy and we'd start running that union find algorithm to start combining these nodes, because we know when we start combining these nodes, if it's possible and they are a part of the same set, that must mean there is a path connecting them. And we know for sure there's only one path connecting them. So what we're going to do is we're going to start at the smallest value and we're going to see how many good paths are there starting at a value of 1. So what we're going to do is we're going to iterate through all nodes with a value of 1. We're going to start with this guy. Remember what we're trying to figure out. How many good paths are there starting at a value of 1? A good path means we can only travel to adjacent nodes with values less than our starting value. Both of these are greater, so we can't do anything starting from this guy, so it's basically nothing we can do at this point. Our union find is pretty boring. We haven't really combined any of these nodes. Next, we're going to go to this node. It also has a value of 1. And we're going to go through all of its neighbors. It just has a single one. It has a value greater than 1, so we can't really do anything with it either. So far, again, our union find is pretty boring. We just have these single nodes that are not connected to anybody yet. So what we determined is that there's 0 good paths starting at a value of 1. This is what I mean by being greedy. We know for sure if there was a path, we would have found it, but there wasn't. So next we move on to 2, and there's only a single value with 2. So now we start going through its neighbors and combining them if we can. It has a neighbor over here with a value of 3. That's greater than it, so we can't do anything. We can't go in that direction. It has another neighbor over here with a value of 1. That's good. So we do combine these 2 nodes in our union find data structure. We combine these 2. We say they are now a part of the same set. So this formed a connected graph. We look at our last neighbor over here and do the same thing. It has a value less than 2, so we now combine this. So now these 3 are a part of the same graph. Now, lastly, we're going to go through all nodes with a value of 3. Let's just arbitrarily start at this one. Now let's start going through its neighbors. We're trying to figure out how many good paths are there starting at 3. There were 0 good paths starting at 1, 0 good paths starting at 2. Even though 2 was connected to some nodes, none of them had a destination value of 2. So starting at 3, we go to this neighbor over here. It has a value less than 3. So yes, we can connect them. I mean, this isn't a good path yet, but we have connected them. And then we would go through the other node with a value of 3 down here and start connecting it with all of its neighbors. It just has a single neighbor over here with a value of 2. That's less than 3. So we can combine them. And after now that we've gone through all of these, now we're going to ask ourselves, how many good paths are there in our data structure with a starting value of 3? Well, remember, this is going to be a part of a union find data structure, and we are going to be able to determine how many 3s are a part of this data structure. And we would see that there are 2 3s in our union find data structure. That means there is a good path. There is one good path starting from 3 and ending at 3. Now, there's one last edge case that I think is kind of dumb. It's not really an edge case, actually. It's just kind of how this problem is defined. A good path technically can be a single node itself. Like just kind of cleaning this up, this itself is a good path. It has a starting value of 1 and it has an ending value of 1. I think that's kind of dumb. So what we did with our algorithm is determine that there was just a single good path in this graph, but there's also 5 good paths, 5 additional good paths, because we have 5 nodes in this graph. So we say that the true answer is 1 plus 5. And you can see that that's what they also had in the solution. I think that's kind of dumb, but that's just how it's defined. So we'll have to go with it. So actually how this algorithm would have worked, we would have started at 1. We would have seen this is our union find. After iterating through these, then we would go through every node and check how many nodes in this disjoint set have a value of 1, just 1. So that's what we would add to the result. How many in this set have a value of 1, just 1. So we would say our solution so far is 1 plus 1. And then when we got to 2, we would do the same thing. And then when our disjoint set looked like this, we would do the same thing. How many nodes with a value of 2? 1. So we'd say our solution so far is 2 plus 1. And then adding these two, we'd say, this individually is a plus 1. This individually is a plus 1. And then the path connecting them is also a plus 1. So we end up with a total of 6. The main improvement here is with union find. Generally, union and find operations are of log n time complexity if you can implement it pretty efficiently. But analyzing union find time complexity is pretty complicated. But generally, it's safe to say that a solution like this one is n log n time complexity. It's not a huge improvement compared to n squared, at least just looking at it like this. But in terms of runtime, generally n log n is much faster. Okay, now let's code it up. So I already created our union find data structure because I don't want to spend too much time on it. There's nothing fancy about this. We have our constructor here where we're keeping track of the number of nodes we're given n, and for every node, we have its parent, which this is going to be an array from 0 to n minus 1. And for every node, we have its rank, which initially is going to be 0 for all of them. You don't actually need to implement union find with union by rank to pass on Leetcode, but this is a slightly more efficient way to do it. We have a find operation. Find basically finds the root parent of a single node. So given a node I, we're going to find its root parent and then return that. Union is going to try to union 2 nodes together unless they have the same root parent. In that case, we're just going to return. Otherwise, we're going to union those 2 disjoint sets together. I think you also don't need to return true and false in this case, but I have it here anyway. You could condense this a lot, but let's move on to the main problem now. The first thing I didn't talk about much was that we do need an adjacency list. For every single node, we need to create a hash map of a mapping. So what I'm going to do in Python is create a default dict where the default value is going to be a list or an array. And then we're going to go through every edge. So every edge has 2 nodes, A and B, connecting them together. And we're going to say A is adjacent to B and B is adjacent to A. This is just so we can traverse through the neighbors of every single node. And remember, we're also going to need to create that value to index mapping. So this is also going to be a hash map, collections.defaultDict, that is going to have a default value of a list. Because remember, there could be multiple nodes with the same value, and we want to group them together. So in Python, you can do this like this for I val in enumerate the values. So this will basically give us the index of every value in this array and the value itself. And I'm going to then say in our value to index map, we're going to take the value, which is the key, and then append the index of the node. And that's pretty much it. Now remember, the result we're trying to get here is how many good paths there are. Initially, I'm going to set that to 0. We also need to create our union find data structure. We have to initialize it. What are we going to initialize it with? Well, how many values do we have? Well, we can just take the length of values to do that. Now we want to iterate through our value to index map, but we want to iterate through it in sorted order. So an easy way to do that is to say for val in sorted, and then take the keys of that hash map by doing this, And then we're able to iterate through these in sorted order. Well, these are the keys. Now, each key could have multiple nodes that we appended to it. So we're going to then go through every single node. So for I in range, val to index, and then use that key. And this will give us a list that we're iterating through. And then we have a third nested for loop. We're going to go through every neighbor of this node. Good thing we created our adjacency list to do that. So for this node, we're going to go through every neighbor. And what we're going to try to do with our union find data structure is union these two nodes together, neighbor and I, if it's possible. We don't really care whether it was or not, because I'll show you what we're going to do later on. And actually, one thing I forgot, we can't try to union every single pair. We can only union, we're starting at I, but the neighbor has to be less than or equal to I for us to be able to union them together, remember, because we're trying to be greedy here. Now, here's where the tricky part comes in. What I'm going to do here is create a count hash map. I'm going to do collections.defaultDict here and then give it a default value of int. That means if we try to say here a count of some key value I is equal or add to it like 5, that means if it wasn't initially assigned, it will have a default integer value of 0, and then we'll add 5 to it, so it will initialize as 5. That's basically so we don't get an invalid key error. But the more important thing here is that notice how we went through all values, we went through all nodes with this particular value. So what this counter is going to do is for each disjoint set, how many vals does it contain? That's the question we're trying to answer. When I say val, I mean this particular value. And let me quickly show you the drawing for that. Let's say that in this case, our value was equal to 3. And let's say that this is something like what our disjoint sets look like so far. We have like a 0 over here, and we have a 3 as a child. This is what our union find data structure would look like if you're familiar with it. And maybe we have a 2 here, which is not needed. And maybe we have like another 3 in this disjoint set, and we have a second disjoint set over here with just a single 3, and maybe over here we have a 3 and a 2 and another 3. So we have 3 disjoint sets. The question we're trying to answer is, for every single disjoint set, how many 3s does it have? Just looking at it, it's pretty simple to figure out, but how would we do it in terms of code? Well, that has to do kind of with that union find data structure. I hope you're familiar with it if you're watching this, but basically we would go through every 3 node in this graph, and we'd say, okay, find the parent of this guy. Okay, it has a parent of this. Then go through this guy. What's its root parent? I'm not just talking about this parent. I'm talking about how far up can we go the chain. And it also has a root parent of this. That's how we would know this disjoint set has 2 3s in it, because both of these guys have the same root parent. So this one has 2 3s. Well, this one just has a single node, so it's pretty obvious to answer, but we would follow the same algorithm we did here. This has a single 3, and this one also has 2 3s. What's this guy's root parent? Well, it can't really go any further up, so it's itself, and for this, its root parent is this. So these two have the same root parent. So this one has 2 3s in it. So now how does this help us determine the number of good paths? Because that's ultimately what we're trying to answer. Well, if this disjoint set has 2 3s, it actually has 3 good paths. This node itself, and then the path connecting them. If this has 1 3, it only has 1 good path. If this has 2 3s, it also has 3 good paths, just like this one. So the total answer would be 3 plus 1 plus 3, which is equal to 7. But in terms of the algorithm that we're going to do, we're actually going to do something clever, because imagine if this one actually had another 3 over here. Then can you tell me how many good paths it has? Well, 1, 2, 3, 4, 5, and 6. So what's the algorithm to determine, since this has 3 nodes, how do we know it has 6 good paths? How can we compute that? Well, as we iterate through these 3 nodes, we'd say, okay, one node here has this root, so we say plus 1. Then we'd find this node and go up here. Then we'd say, okay, this has 2 3s so far. So then we'd say plus 2. And then from this one, we'd say now this has the same root. So there's 3 3s here. Then we'd say plus 3. That's the algorithm. If we had a fourth one here, then we'd say plus 4. Because every time, notice how every time we introduce a new 3, if I introduce another 3 over here, how many new good paths did I just create? 1 connecting these two, 2 connecting these two, 3 connecting these two, and then 4 connecting this with itself. So every time we introduce a new node in the same disjoint set, we're adding however many nodes we have total. That's how many good paths we're creating by doing that. I know this is really complicated at this point, but that's why this is a hard problem. So to wrap this up, mathematically, if this disjoint set had n 3s in it, or whatever unique value we care about, then how many good paths does it have? Well, 1 plus 2 plus 3 ... all the way up until n good paths. That's kind of the algorithm generally. Now let's finish up the code. So now to finish this up, since we don't have direct access to every single disjoint set, what we're actually going to do is go through every node with this particular value. How can we do that? Well, that's what we created our val to index map for, and we're going to give it a key of the value again. So pretty much we're doing the same thing that we did up here. And I just realized I have the range function here, which we definitely don't need. We just need to iterate through the values themselves. And here I'm going to go ahead and add in. And for the index, I don't need to use j because that's not taken. We can use I. I'm getting a bit flustered, but using this node, we want to know what is the root parent of it. So with our union find, we can say, find me the root parent of this. And with that, we want to increment the count using this root parent. We want to know this basically identifies a disjoint set for us. And now we're going to increment that count by 1 because we know that this node is a part of this disjoint set. And we're going to take this count, just like I talked about in the drawing, and then increment our result with that value. And we probably don't need to call union find multiple times here, but it doesn't really make a difference. We could have just stored the value in a separate variable, but it wouldn't really change anything. Oh, and sorry, another bug I noticed is that the neighbor does not need to be less than I. These are the indices of each node. We actually care about the value. How can we get the value? Well, we were given a vals array, so we can map this neighbor to the value, and we can map this original node to the value. We can only union 2 nodes if the neighbor is less than the original value, or equal to, of course. So with all that done, we can now, after we exit the for loop, go ahead and return the result that we computed. Let's run this to make sure that it works. Oops, I called this val instead of vals. Sorry about that. Hopefully we don't have more typos. And as you can see, it works and it's pretty efficient. I want to quickly touch on a last point. My first solution, I actually went wrong somewhere, and I think it's worth discussing how. Initially, I didn't create this val to index map outside here, and I created it inside here. And you might think, wouldn't it be better to not have these 3 nested for loops? Why do we have to iterate through every node with the same value before we execute this part? Well, it has to do with one of Leetcode's test cases, which if you coded it the other way, you didn't have these 3 loops here, and you just basically went through every node up here, but you still did it in sorted order. This portion would actually end up being n squared. And the test case is, what if every single value that we were given was the exact same? What if every value was 1? And this is specifically the code that I'm talking about. This is the code I first tried, but it didn't work. And the reason it doesn't work is, what if the test case we're given has a bunch of 1s? We have the exact same value for every single node. Then what would happen is we iterate through a node with a value of 1. Then we go through all the other nodes with a value of 1 and see if we can union them together. If we can, we increment the result by 1. And then on the next iteration of the loop, we're going to reach the second one, and then we're going to go through all the other ones and see if we can union them together. Whether we can or not doesn't matter, because this loop is going to execute n times, and this loop is going to execute n times, and then we're going to get n squared. Whereas with this solution, if we had the exact same value for every input node, this outer loop would only execute a single time because we only have one key value. We only have a single unique value. And then this loop would execute n times. We do have our find function here, so we'd still end up being n log n, but that's not too bad. Much better than n squared. So if this was helpful, please like and subscribe. If you're preparing for coding interviews, check out Leetcode.io. It has a ton of free resources to help you prepare. Thanks for watching, and hopefully I'll see you pretty soon.